Welcome to TeleGeography Explains the Internet, the show that explores the business behind all of the ways humans stay connected around the world. I'm your host, Greg Bryan, and today we have a bit of a different episode. We've perhaps a bit audaciously called this podcast TeleGeography Explains the Internet. So in this special 5-part series, we're going to attempt to do just that, to explain how the internet works and dig into the business behind pushing bits around the world. Rather than my normal free-form interview format with some outside expert, much of these episodes will be me going solo to explain various aspects of the telecom business. And in each episode, I will seek the help from some of my colleagues who are experts in the area I am covering in that episode. But our goal here is to pull back from maybe the day-to-day jobs that many of you have and highlight the nuts and bolts of how the whole industry works together as a broad ecosystem. It may be an overused word, but it's really the best one to describe all these different parts that work together. So my hope is that you might save these episodes for reference, pass them on to friends or colleagues that want to know more about telecoms or how the internet works. So to give you a quick preview before I jump into episode 1 here, we've broken out 5 episodes, each answering a different question. So this episode is how does the internet work? Next, we'll talk about what is the transport network. Episode 3 will be what are data centers? Episode 4, what is the cloud? And episode 5, what is a WAN? So that gives you a little preview of how we're breaking everything up and exactly what we're going to be talking about of that big picture of how does all of this actually play out together. Of course, all of those episodes, particularly the first one, are huge questions that we could never begin to comprehensively answer in a brief podcast. But I hope to give you just a good foundation for understanding the basics. There are many books or resources, of course, that you can find if you want to dig deeper. One at the start of the series that I would specifically recommend is Tubes by Andrew Blum. Not only does it feature some of my telegeography colleagues, but it provides a readable and personality-filled explanation of how the internet came to be and how that influenced the way that it works today. There are, of course, lots of other resources that you can find out there on the internet. All right, so let's dive into our question this week. How does the internet work? When I started thinking about this, really the question that we want to ask is, how does data move from one computer to another? And I'm not going to go into the whole long history. Like I mentioned before, you can read books about that and understand all of the roots of this. And that's helpful to understand some of these things. But I want to focus on, what we call the internet sort of today and what's actually happening when you use it. So where we're going to start is in binary and packets. Okay, so the internet, of course, is a network of computers, and computers can only understand 2 things, on and off. So everything that we do in the internet is in binary, or a series of ones and zeros representing on and off that give instructions to your computer to do all of the amazing things it does. I suspect everybody listening to this show already knew that, but it's good to start at that foundation. That means that the very bottom of the internet is just a system of sending ones and zeros over wires, or in some cases, spectrum. Whatever you do in the internet, email, video, chats, listening to podcasts, that information is translated into ones and zeros by your devices and then transmitted in what we call packets or data packets. And a packet is simply a bundle of ones and zeros with a header that tells it where to go, what type of data is inside, and any kind of special information about the content necessary for its journey. Everything that goes over the internet is separated into packets of data that move through the tubes of the internet, or the transport corridors. So as I'm recording this podcast, my voice is being digitized into ones and zeros by my microphone and computer. Those ones and zeros will be separated into packets, sent to our podcasting host, stored, and then sent back to you when you're listening. Those packets then get reassembled in order by your computer so that it sounds like I'm talking to you. Now, when I wrote all of that out, I really started thinking, for anyone who thinks that our world is kind of devoid of magic, when you break it all down that way, electrical engineering and the things that we've achieved with it, I think can make your favorite fantasy book look positively banal. It is truly incredible, right? So when we're talking about how to move bits around the world, you are often going to run into something called the OSI model. So we're really focused on layers 1, 2, and 3, but let me explain all of that. So the OSI model splits computer networking into 7 layers. It's a conceptual framework. And like I said, we really focus on layers 1, 2, and 3, which are called the physical layer, the data link layer, and the packet layer. In practice, in my experience, people in the internet industry rarely use these actual names, but simply call them layers 1, 2, and 3. So let's talk about each of them very briefly. And again, I'm giving you a really quick, high-level version of all of this. You can dive much deeper and get much more technical than I have the ability to discuss here. But this will give you an idea of why we break all these things out this way and what it means for how the internet works. So layer 1 is the layer where the physical transmission of data happens. So in other words, whatever the medium, that could be fiber optic cable in many, many cases, copper of some kind, that twisted pair, coaxial, Ethernet cables, or spectrum if it's going through the air. This is where the bits are essentially turned into light in order to travel from one place to another. At layer 2, a network establishes a connection between two specific nodes on a single network. So, of course, during its journey, your data is going to go across possibly very, very many nodes. Many folks in the telecom industry, in my experience, use layer 2 interchangeably with Ethernet. Although I should point out there are other layer 2 protocols. So layer 2 and Ethernet are not exactly the same thing. In other words, Ethernet is layer 2, but layer 2 is not necessarily Ethernet. Now, if you are like me, over the age of 40 or so, you are likely familiar with a Cat5 or a Cat6 cable, also called an Ethernet cable, that was once directly connected to your computer to connect it to the LAN or local area network. And Ethernet originally was a local area network technology. I'll get more into that in a later episode, in the transport episode. But just, real quickly here, for a long time, Ethernet was a LAN technology, and then carrier Ethernet was developed to use it over long-haul transport. But in terms of the internet, layer 2 uses frames, which are containers that hold the data packets we will talk about in layer 3. This is also the layer that hosts MAC addresses. You've probably heard that term before. That's just the way to identify individual devices connected to a network. So a MAC address identifies your device locally, while its IP address, we'll talk about that in layer 3, identifies it on the global internet. So layer 3. Layer 3 is really what we think of as the internet, at least colloquially, right? And it's the ability to have these any-to-any connections across a mesh of network links. Layer 3 is where packets of data get routed across this mesh network to reach their final destination. So this is the layer where you use IP addresses, which really function as kind of a street address or telephone number of the packets you're sending or receiving. Where are they going to go on this network? Your data packets are going to travel across very often many different networks owned and maintained by many different companies or organizations. And it's in this layer 3 that allows your data to randomly zip across this network of networks that make up the internet and still get to where you wanted it to go. So you've definitely heard of IP, or Internet Protocol. This is simply the method of defining the addresses needed to route traffic over the internet. If you've ever done a what is my IP search to get through a firewall or something like that, you might have seen that it often comes up with two IP addresses, IPv4 and IPv6. I'm sure many of you in the telecom industry have heard lots and lots and lots about this. Anyway, But really, the only difference between those two things is the length. IPv4 is 32 bits and has a mathematical limitation of about 4.3 billion addresses, which, as you can guess, is far, far too little for the number of devices now connected to the internet. Most of the world is connected to the internet in some way, and there's 8 billion of us, and most of us have many different addresses. So we had to move to IPv6, which is 128 bits, to provide way more than enough digits to accommodate devices for the foreseeable future. So, the internet is a network of networks. What that means in practice is that all across the world, thousands of separate organizations, mostly for-profit companies, have built out networks using these standard protocols, and they exchange traffic with each other. When a packet of data leaves your computer, it has a destination in the IP address. But how it gets to that destination is really actually very random. And that's what makes the internet different than some other telecom services, like a point-to-point line where your traffic is going in a predefined path that is maybe belonging only to your organization. Many factors make up the performance of the various networks when that packet is sent. And so that is another important feature of how the public internet works. So in other words, unlike a traditional phone call, which going back to the 19th century would create a direct circuit switch link between two callers, an email you send is broken into many, many packets, and those packets might take very different physical paths across the mesh network of the internet, get transferred through different routers, even different networks, before they arrive at their destination and are reassembled by your computer or someone else's computer on the other end. So how and where these networks are connected to each other is actually part of what we cover at TeleGeography in our IP Networks Research Service. And since I have personally never worked on that project, I wanted to invite my colleague Tim Strong on to answer a few questions about how networks interact with each other. Welcome back to the podcast, Tim.
Thanks, Greg.
All right. So as I've been explaining, I really wanted to break down exactly how the internet works. That gets a little bit outside of my research areas at TeleGeography, or a lot, really. So I wanted to have you on so that I could ask some of these more detailed questions that I just don't deal with very often. So thanks for doing this.
Sure.
All right. So first, I just want to talk about how traffic actually moves around the network, where we've been breaking it down to the most basic levels. So just how do bits move across the network?
Yeah, that's a great question to start on because I don't know if you meant to or not, but it really gets to the heart of what the internet actually is. You asked about how traffic moves around the network, as in singular. But in fact, there's no single monolithic network. Instead, what the internet is a series of interconnected networks. Right now, there are over 100,000 interconnected networks that make up the
I didn't know it was that high. That's really cool. Yeah.
Yeah, there are an awful lot of them. And what makes the internet are the commonly agreed upon protocols that link all these networks together.
Mm-hmm.
And I find it helpful to have a concrete example when explaining the internet to, say, family and friends who ask about it. Let's use this specific podcast as an example. Neither of us are in the office right now. Today, we're both happen to be working from home. So we're recording this portion of the podcast from our homes. And I just ran a trace route to your home's IP address.
Mm-hmm.
At my house, I use Comcast as my home internet provider, and you appear to use Verizon Fios.
That is correct. Yeah.
Comcast's ASN, which we'll explain in a minute, is 7922. Verizon's ASN is 701.
All right.
According to the trace I just ran, my packets start at AS7922, which is Comcast. Good. And then the packets are handed off to your ISP, AS701, aka Verizon. And this is a really simple example. It involves just two networks involved, but sometimes there are a lot of networks. And I also wanted to add, if they're nerdy enough to listen to this podcast, Greg, your listeners may just be nerdy enough to want to try this out on their own. So it's super easy to do. You just open up a terminal window on your computer. You type in traceroute space hyphen or dash a space, and then either an IP address or URL, and it will show you in the first column all the ASs it traverses, and then the different hops. It's
That
kind
is
of
really fun. I've done that many times on business trips when I get to my hotel. Right, it's kind of just fun to see, and it's often surprising. So in our case, we are geographically very close to each other, and we're near Ashburn, which has a lot of connectivity, so it makes sense. But very often, you're gonna, as you say, hit way more than two networks.
you sometimes hit more than two networks, and sometimes it goes in weird directions.
Hmm.
Even though you and I are just across the Potomac River from each other, west of DC, so where our homes are,
Hmm.
I noticed that my packets actually went to Capitol Heights, Maryland, which
Mm.
is on the other side of DC, via Comcast before going to Ashburn, and then went to your home. So it went almost in a 180-degree boomerang.
Yeah. Yeah. And then you can imagine how globally that gets really complex when this is just, as the crow flies, just, I don't know, what, 50 miles or so, right? And not even that.
Absolutely.
Yeah.
Yeah.
So, all right. So you mentioned ASNs. What exactly is an ASN, and which providers actually need one?
Sure. So ASN stands for Autonomous System Number. It's basically the primary identifier of an independently managed network on the internet. And the basic rule of thumb is if you need to connect to two or more specific networks, you probably need an ASN. That
Hmm.
means you need some sort of routing policy. If you need to have a routing policy, you need an ASN. In practice, what that really means is that nearly all ISPs have their own ASN. And lots of hosting providers have them. Universities often have them, and so do some large enterprises.
Hmm.
Individuals like you and me don't need an ASN. We'll just rely on our own ISP to route our packets for us.
Yeah, and as you point out, among corporations, only a very large ones, and even among them, there are ones who do networking in a particular way. So it's really not something that is broadly held among internet users out there.
Correct, not individual users,
Hmm.
maybe some really geeky ones.
Right.
But for enterprises, if they want to have a lot of control over their IP routing, they often will
Hmm.
register for an ASN.
Hmm. All right, then when we're getting to how those networks talk to each other, often what's going to come up is BGP. And I'm in part of this whole series, I'm trying to cut through what I like to call, the alphabet soup, and make sure everybody understands what's behind those. So, what does BGP stand for, and why is it important in routing traffic over the networks?
So BGP stands for Border Gateway Protocol. It basically tells ISPs or anyone who has an AS which other ASs it has to go through to reach an IP address.
Mm.
Um, it basically provides the rules for routing your traffic. So you, the user, provide your ISP a destination IP address when you type in a URL. That's pretty commonly known.
Hmm.
But how does your ISP know how to reach that address? What if they don't directly connect to that AS?
Mm.
That's where BGP steps in. The provider they're trying to reach publishes a list of all of its IP address ranges, and next to each IP address range or IP address, a series of ASNs that can reach it. And you have to go kind of in that order of the
Mm-hmm.
ASNs that are listed. To route your traffic, your ISP looks up the IP address against that published routing table to determine through which ISPs it routes your packets. On the internet, a full version of the entire internet's BGP table entries is millions and millions of lines long. It's
Mm-hmm.
gigantic at this point.
But presumably millions of lines long, still easy enough for all of these routers and intelligent kind of systems to parse, basically, right?
Yep.
So, yeah,
Yep. It works pretty well.
yeah, amazingly well when you think about all of the bits that are in flight all the time, right? So, all right, so that's kind of how the bits actually move across the internet. Now, how do these different, as you said, hundreds of thousands of different internet providers of various sorts, how do they actually exchange traffic with each other? So, in other words, we know there's something called an internet exchange. What goes on at an internet exchange?
Okay. So far we've been talking about the software or protocols used to interconnect networks. But the internet is also a physical thing. It's not a cloud, but it's basically a bunch of computers connected by a whole lot of wires. Let's say you're an ISP. If you need to interconnect with another network, you'll need to find a physical location where both of you are present, where there are computers or routers that can exchange the traffic.
Mm-hmm.
That may mean that you go to the other network owner's premises. But to make things more efficient, there are these things called internet exchanges, and they're also called internet exchange points. So sometimes you see IX or sometimes you see IXP. It's the same thing.
Mm-hmm.
Those are purpose built for exactly what it says on the tin, exchanging internet traffic. Usually, an internet exchange is hosted at a third party data center, and lots of other networks already connect there.
Gotcha. Okay. So just to reiterate that there could be situations though where it's not even happening at an IX or IXP, but that there's some location where those two networks decided to interface directly with each other as well.
Yeah. In the case of this podcast, it may well be that Comcast goes directly to one of Verizon's
Mm-hmm.
facilities and they
Mm-hmm.
completely skip a third party data center
Right.
altogether.
Because they know they have eyeballs in the same region and they're going to be exchanging a lot of traffic with each other. Okay.
That's right.
So then, within that context of ISPs and backbone providers exchanging tons of traffic with each other, we often run into terms like peering. So, if you could explain maybe IP peering and what internet providers do to engage in that with each other.
Okay. So peering is an agreement between two networks to allow each other access to their own networks. Usually this is free, but some of the big guys charge a fee for little companies to get access to its network. Internet providers engage in peering in order to widen their access to the entire or to the wider internet.
Mm-hmm.
Let's say you're an ISP just starting business. You're starting from scratch. At that moment in time, you'd only be able to route traffic among IP addresses of your own customers. You wouldn't be able to get them anywhere else on the internet.
Right.
If you peered with other providers, that would allow you to route customers' traffic to those other providers too.
Gotcha. So it opens up the network of networks to your eyeballs, to your customers, essentially.
Yes.
All right, then we also are often going to hear in this similar kind of space about IP transit. So what's the difference between peering and IP transit, and when do IP providers use transit instead of peering?
Okay, a couple of differences. One is IP transit is a paid service.
Mm-hmm.
As far as I'm aware, it's always a paid service.
Mm-hmm.
The other thing is if you buy IP transit, the provider of the service will give you access not just to its own network, but also to the networks of its other customers and peers.
Mm-hmm.
Now, usually the price for IP transit is quoted per meg. I know you're a huge fan of that movie. It's really well done. I agree. Oscar quality. But here we're talking about megabits per second, not
Right.
the chart. So the price per megabit per second. The way that works is that you will bring your traffic to a specific geographic location, like some agreed upon data center or internet exchange.
Right.
And then there you commit to a certain traffic level. You'll be quoted a price per meg. That's the price you'll pay your IP transit provider each month. For example, a price of 20 cents per meg on a gig-E port, so that'd be 1 gigabit per second,
Mm-hmm.
would be $200 per month. That's because a gig-E is 1,000 times larger than 1 megabit per second, and 1,000 times 20 cents is $200. I double checked the math.
Yeah.
Yeah.
Yeah. At least we kept it simple there. I should say I remember a time when IP transit was often in dollars. It was very easy to figure out. Then it's gotten much more cheap over the years, and it's now in fractions of cents in some cases, right? So it
Yeah, it
becomes
is.
a little bit more difficult to calculate. But that was excellent, Tim. I think that cleared a lot up for honestly for me, and will fit in well with what the story I've been trying to paint of the internet here. So thanks so much for the help.
You're welcome. It's really boring.
Yeah.
Oh, wait, Jay will fix that in post.
Yeah. I think everybody listening here kind of wants to know how this works. So now they know a little bit more.
No, it's actually pretty cool.
Yeah. Cool. Thanks, Tim.
Thank you, Greg.
Okay, that was really helpful for me. Thank you to Tim. But before we wrap up, a quick word on other internet protocols. In this episode and in telegeography's work in general, we focus, as I have said, on layers 1, 2, and 3, but many internet protocols happen at layers 4 through 7. Again, maybe something you want to take a deeper dive in if you're not super familiar already with the OSI model. But just real quickly, I'm not going to talk on this series about things like TCP, FTP, HPPT, or any of the other numerous alphabet soup combinations that explain exactly how data are transmitted. Our task in this 5-part series is really to talk about the physical infrastructure of the internet and the business around pushing bits through it. But that, of course, is a fascinating topic and one for which hundreds of resources are available if you want to take a deeper dive, of course. So, to wrap this up, I thought it would be fun to have a little example to illustrate how the internet works. So, this is an example that I think we'll all be familiar with. And at the end of each episode, I'm going to relate what we've talked about to the life cycle of a YouTube video. So even if you've never uploaded a video to YouTube yourself, you have very likely watched some creator, possibly working from, say, a home studio like I'm in now. And that's how I have envisioned this example. So, our content creator films themselves doing something, let's say demonstrating a guitar riff, skateboarding, or maybe folding some particularly complicated origami. And the sights and sounds that they are making are converted by their camera and mic into ones and zeros and then downloaded to their computer. Then our content creator goes on and edits things. And once that's done, they upload the video to their YouTube account. So their computer is going to break that video up into packets, bunches of ones and zeros. Each of those packets will be tagged with an IP address that will allow networks to direct those packets to this content creator's server space on YouTube servers, probably located in the most local Google data center, or I should say Alphabet data center, I guess. So the content creator's local internet service provider, that's, Comcast or Verizon, like in Tim and I's example from earlier in the episode, they will be connected with Google using their ASN, and the packets will be on their way to Google servers living in this data center. Now, depending on where our content creator actually lives, as we discussed with Tim, this journey might take the packets on a very simple path, say between only a couple of providers that exchange their traffic directly with each other. Or it might go through this long path around different directions and through many different networks using those connections, that ASN and BGP, and how that all routes traffic to get from the content creator's local network all the way to the Alphabet servers. Now, once those packets arrive at one of the closer Alphabet or Google data centers, then that content creator's video will be indexed for search so that people can find it. And then again, separated into packets to be spread now across the YouTube network so that the content creators' viewers from around the country or even the world could potentially access that video without the latency that would result if the video was only stored in the content creator's local data center. So the packets have now done this same journey, again, using different IP addresses and crossing across different providers' networks through IP peering and transit agreements to get to one of the many locations around the world or perhaps around the region that YouTube stores videos. Then, once a viewer sees that there's a new video on their content creator's page and hits play, the data center that's closest to that viewer is going to get pinged, and it's going to start that journey all over again, splitting the video into packets, sending them across whatever networks it needs to cross to get to that viewer's ISP, and then finally reassembling all of those packets on the viewer's device. So once again, those packets will take maybe a random kind of journey across many different networks, just to be all reassembled again on the other end at this viewer. So that is essentially how a YouTube video gets from its content creator to you. Now we're going to get deeper into the different legs of that journey as we go deeper into our segments about the internet. All right, so I hope you enjoyed the start of this series. If you have ideas or thoughts or comments, please let us know.